Hello guys, in the previous video we have discussed some example questions on stationary waves. So let us discuss few more questions now. First question, a string fixed at both ends is in resonance in its second harmonic with tuning fork of frequency f1. Now its ends become free. If the frequency of the fork is increased slowly from f1, then again resonance is obtained when frequency is f2. If in this case the string vibrates in nth harmonic, find the value of n and f2. So here in the first situation he has given that string is fixed at both ends. String is fixed at both ends. So here it should form a node and here also it should form a node definitely. Okay, now he is talking about second harmonic. Second harmonic means there will be two loops in it. So here you have node at midpoint and this is how the oscillations will look. So now in this case let us say length of the string be L. So its frequency will be, fundamental frequency will be 1 by 2L into under root T by mu, but this is second harmonic. So now frequency of the second harmonic will be 2 by 2L into under root T by mu. This is the expression for frequency of a second harmonic. Now this should be equal to the frequency of the tuning fork. So here frequency of the tuning fork is given as F1. So this should be equal to F1. Okay, this is what we got from the first situation. Now in the second situation, so this end, one of the end becomes free. So in this case, if you consider the string, it becomes a free at one end. Means, so let us say this part is fixed and this part becomes a free. So everything is same, right? Here, now it has to form antinode at this position. Here it should be a node and here it should be antinode. So now what are the possible oscillations? So the possible oscillations are this one. So this is the first possible oscillation. String can oscillate like this. So between these two amplitudes. Next possible one. In this case second harmonic is not possible as it is string fixed at one end, free at other end. Right? Always it forms only odd harmonic. So the third harmonic. So third harmonic, if you look at it, so we have one node here and this is how it oscillates. So this is the second possible, first O-tone or third harmonic. Next possible frequency or next possible mode, we have one more node. So here we have two nodes. So now it will oscillate, the oscillations will look like this. So this is how the oscillations are possible. Now if I write expression for frequency of this string nav, so let us say it is in nth harmonic. So if I write expression for this, Fn will be n by 4L into under root T by mu. So this is also should be, this is equals to F2. Okay. So now he is saying that when you increase F slowly or F1 slowly, we should get F2. Now let us write what are the possible frequencies of this one. So N should be here. One thing you have to keep in mind here, N has to be odd only. This should be odd number because we have only odd frequencies. So here it should be odd because in case of string fixed at one end, free at other end, only odd harmonics are possible. So now if I write the all possible frequencies, so first if I take n is equals to 1, we have frequency of, it will be 1 by 4L into under root T by mu. Next if I have, if the next possible frequency is n equal to 3 by 4L into under root T by mu. Next possible 5 by 4L into under root T by mu. So this is how you will have. So these are the possible frequencies. Now what is saying, this is F2. Now he is talking about increasing F1 slowly and you'll get F2. Means F2 is next possible frequency from F1. So if I plot F1 here, so F1 value will be, so this one 1 by L into under T by mu, so it will be 4 by 4L, so it will be here somewhere here. So F1 will be here, that is 1 by L into under root T by mu. So now if you increase F1, the next possible one is this one. So this is the frequency is talking about. So if we compare this with N, so here N value will be 5. So if N value is 5, so we can calculate, we can substitute back, you will get F. N value will be 5 and F2 value will be equal to, substitute here, 5 by 4L into under root T by mu. That is 5 by 4 times F1. So this is how to solve this question. The next question, a massless rod is suspended by two identical strings AB and CD of equal length. A block of mass M is suspended at point O such that BO is equal to X. Further, it is observed that frequency of first harmonic of this one, this AB, is equals to second harmonic of CD. So this is the question. Now we have to calculate the length of OB. This length X value we have to calculate. We have to find X. So now here is given two strings are identical, means their linear mass density will be same. If it is mu, here also it is mu, and length of the strings is also same. If it is L, here also it is L. Okay, so next, if mu and L are same of both, and then tension, coming to tension, as this mass is, it is not symmetric, so tensions will be different. Let us say tension in the string be T1, here it will be T2. Okay, now frequency of this one, he is comparing frequencies of these two. So frequency of this one is saying it is a first harmonic or fundamental frequency, so let us say F0, and here it is in second harmonic, so it is F2 or F1, first overtone. Now he is saying these two frequencies are equal, that is the information given. Now we have to calculate X value. So how to calculate X value? So first we have to calculate to X value, we have to use the given information. So always write the given information in terms of equations. So he's saying fundamental frequency of this one and the first overtone of this one are equal. So write it in equation. So first I will find F0, fundamental frequency of wire AB. So we know fundamental frequency as it is string fixed at both ends, node here, node here. So it is string fixed at both ends. So fundamental frequency will be 1 by 2L into under root T by T1 by mu. So next, he is saying it is equals to first overtone here. So first overtone this one, F1, first overtone will be of this one will be 1 by 2L into under root T2 by mu. Now he's saying these two are equal. So equate these two. So from there you will get a 1 by 2L into under root T1 by mu. So this is second or second harmonic, right? So it will be 2 by 2L. So now if I equate it, I'll get a 2 by 2L into under root T2 by mu. So here root mu gets cancelled, 2L gets cancelled. If we square it, you will get T1 by T2 is equals to 4. So this is the expression we got from here. Now we will use this information to calculate X value. So to find X, what we'll do is, as the rod is in equilibrium, rod is in equilibrium. So net torque acting on it will be 0. Now, so I'll write torque due to all the forces. What are the forces acting on it? Here T1 is acting upwards, here T2 is acting upwards, and mg. So torque due to T1 plus torque due to mg plus torque due to T2 should be 0. So if I write the torques, so we know torque is equals to expression for torque as R bar cross F bar. So cross product, how to find the direction of it? First point your fingers in the direction of R bar, then curl your in the direction of F bar, then thumb shows the direction of torque. So now here torque due to T1, so T1 is here, so R cross F, so it will should rotate it like this, so it will be into the plane of the board, so it will be minus, let us take out of the plane as positive, so into the plane will be negative, so minus x into T1 plus, next due to mg, so now about we are writing about here torque, net torque is 0, I am writing about, this is about any point, but I am taking here about O, so as we are writing about this point, R bar is 0, so torque will be 0. Next torque due to this one, so R cross R is in this direction, cross F bar upwards plus, so it will be positive. R distance is, if this is x, this will be L minus x, so R2 will be L minus x, so L minus x into T2 is equals to 0. From here we'll get T1 by T2 as L minus x by x, and we got already T1 by T2 as 4. So from here if I calculate, L minus x is equals to 4x, from here 5x is equals to L, that implies x is equals to L by 5. So this is how to solve the question. The next question, a 60 centimeter guitar string under a tension of 50 Newton has a mass per unit length of 0.1 gram per centimeter. What is the highest resonance frequency of the string that can be heard by a person? See here, person will be able to hear only up to 20,000 hertz. So he's asking the highest frequency below 20,000 hertz. So now, as it talking about guitar string, so the string will be fixed at both ends. So it will be fixed at both ends. In guitar, the string will be fixed at both ends. Now, what are the terms given? He has mentioned tension in the string as a 50 Newton. Next, he has given length as 0.60 centimeter. 60 centimeter can be written as 0.6 meter. Next, mass per unit length, the mu value is given as a 0.1 gram per centimeter. So I can convert it into kg per meter. So it will be 0.01 kg per meter. So I'll multiply by 100 and divide by 1000. So it will be 0.01 kg per meter. These are the terms we got. So now from here we can calculate fundamental mode of this one. Means the minimum possible frequency with which it can form stationary. Means this is the fundamental mode. So for fundamental mode I'll calculate the frequency, and all the harmonics will be multiples of this fundamental frequency. So first let us find fundamental frequency. So fundamental frequency will be 1 by 2L into under root T by mu. This is the expression for fundamental frequency. So if I substitute the values, be 1 by 2 into 0.6 into under root 50 by 10 power minus 2. So from here if we calculate this one, we'll get F0 value as, it will be approximately 58.926. I have calculated it separately, so you can solve it and you will get it. So F0 will be 58.926. Now all the harmonics here means the next possible frequencies in this. Next possible frequencies in this should be like this. So this is the second one. So all these harmonics will be multiples of this F0. So F, the frequencies will be multiples of, let us say nth harmonic will be n times F0. So the frequencies possible are 58.926 into n. Now these are the frequencies possible where n is from 1, 2, 3, 4 so on. Now he is talking about audible sound. Means this Fn should be less than, F should be less than 20,000. Now let us check it, what is the maximum value of n for which F will be less than 20,000. So let me substitute it here. So if I substitute, you'll get 58.926 into n less than 20,000. If I calculate n will be less than 20,000. by 58.926. Now we have to find maximum value of n such that it will be less than this one. So this value, if you solve, you will get it as some around a 339.4 something. So here the maximum value of n is 339. So this is the maximum frequency or maximum harmonic we can hear. So now let us calculate the maximum frequency which we can hear. So F maximum will be 339 into 58.926. So this frequency which you can hear, maximum frequency which can be heard is 339 into 58.926, and its value will be approximately 19,976. So approximately. So this is how to solve the question. Next question. A light string is tied at one end to a fixed support and to a heavy string of length L at the other end as shown in the figure. So this is how they have tied a light string and a heavy string. Mass per unit length of this string is given as mu, and that of this string is given as 9 mu. So tension will be same as these two are connected. Tension of both the strings will be same, it is T. Find the possible values of frequency such that first case point is a node and second case it is node, antinode. So let us find it for node separately and antinode separately. So now here if we compare these two strings, here tension in both the strings should be same. So tension of first string and tension of second string would be same, both are T. So tension of this is T and this also is D. Next, as these two are connected, they will resonate or they will oscillate with same frequency. So frequency of both the strings must be same. Okay. Next, as mass per unit length of this first string is mu and second string is 9 mu, right, the velocities will be different. Let us say velocities on this string be v1 and this be v2. So if velocities are different and frequencies are same, your wavelength will be different. Wavelength of the string and this string will be different. Let us say it is lambda 1 and lambda 2. Now as wavelengths are different, the number of loops here and here should be different. As wavelengths is different, number of loops will be different. So let us say it is oscillating in a N1 harmonic and it is oscillating in N2 harmonic. Here lengths are given same, both length of this one and this one is same. So here frequencies of both the parts should be same. Now let us calculate frequency of both the parts and equate them. Now first let us take first condition, that is a node at this point. Here definitely it should form a node, here also it should be form a node. Now in the first condition let us take this point A is node. So for node at A. Now let us write the expression for frequencies. So frequency of this part, so if it is node, this string will behave like string fixed at both ends. Then let us say this is in N1 harmonic, so it will be N1 by 2L into under root T by mu. This is the frequency. Next, here if I write it, N2 harmonic, N2 by 2L into under root T by 9 mu. So from here if I solve, 2L gets cancelled, root mu, root T gets cancelled. From here I'll get N1 by N2 as 1 by 3. So number of loops in both the strings has to be in the ratio 1:3. Now let us check the possible cases, possible values of frequencies. So N1 and N2 values. Now if it is 1 it should be 3, if it is 2 it should be 6, 3 it should be 9. So like this. So let us substitute the values back here. So in this case the frequency possible is 1 by 2L into under root T by mu. And next, here F is equals to 2 by 2L into under root T by mu. Next, 3 by 3L into under root. So these are the possible frequencies and so on. These are the possible frequencies for node at A. Next let us calculate for antinode. Next let us calculate for antinode at A. antinode at A. Then the string looks like this. This should be antinode, and here definitely it is node, here also it is node. Now these two strings behave like string fixed at one end, free at other end. Now frequency I can write it here as some, let us say it is in P1 overtone, and here it is P2 at overtone. So now frequency will be 2p plus 1 by 4l into under root t by mu, should be equal to 2p2 plus 1 by 4l into under root t by 9 mu. From here if we solve, we'll get 2p plus 1 by 2p2 plus 1 is equals to, so if I solve it, root t by mu gets cancelled, 4l gets cancelled, so it will be 1 by 3. This is the ratio. The ratio has to be in this form. Okay, so now the possible values are P1 and P2, possible values for P1 and P2 following this ratio. If P1 is 1, so you can substitute the values and cross check it. So you'll get for P1 is equals 1, P2 value will be 4, next for 2, P2 value will be 7, for 3 it will be 10, 4 it will be 13, like that, so on. Okay, so now here I'll write the possible frequencies. So if I substitute 1 here, I'll get F as 3 by 4l into under root t by mu. Next will be 5 by 4l into under root t by mu. Next, in this case it will be, substitute 3, so 3 2s are 6 plus 1 7, 7 by 4l into under root t by mu. So these are the possible frequencies. Similarly, these are the possible frequencies. The next question, a string fixed at both ends is vibrating in lowest possible mode of vibration, for which a point at quarter of its length from one end is point of maximum displacement. The frequency of vibration in this mode is 100 Hz. What will be the frequency emitted when it vibrates in the next mode such that point is again point of maximum displacement? Now here he is talking about a string fixed at both ends, but with a condition. That is, here let us take the string, here we have two nodes. Now he is saying definitely it has to form an antinode at a distance L by 4 from this end. So this is the condition. With this condition, the minimum possible frequency is 100 Hz. Now he is asking the next overtone satisfying these conditions. To solve that, what I'll do is, I'll treat these two parts of the string as a different strings, and then we will cross check what are the possible values of frequencies. So first, if I take this string, as these two strings are connected, the tension in both the strings will be same, T will be same in both of them, and linear mass density will be same because it is a single string. Next, as tension and mu are same, velocity will be same, and we know as these two are connected, frequency has to be same. Now as frequency is same, velocity is same, wavelength of the waves will be same. Next, length of this one is L by 4 and length of this is 3L by 4. As wavelength is same but length of the string is different, so the harmonic in which they are oscillating will be different. Let us say this part of the string is, as it is a string fixed at, we can treat it as string fixed at one end, free at other end, because here it is antinode. So this part we can treat it as string fixed at one end, free at other end. This part also we can treat it as string fixed at one end, free at other end, because it has to be always antinode. So I am treating these two strings as two separate things. Okay, so from there, as it is in it is similar to string fixed at one end, free at other end, we have to take overtones. So let us say it is in P1 overtone and this is in P2 overtone. Now what I'll do, I'll find the frequencies in terms of P1 and P2, and then as frequencies are same, I'll equate. So let us write frequencies of this one. So frequency of pth overtone of this part will be 2p plus 1. We know for a string fixed at one end, free at other end, frequency of pth overtone is given by 2p plus 1 by 4l into under root t by mu. So it is 2p1 plus 1 by 4 into length of this one is L by 4 into under root t by mu. And similarly I'll write for this one. So it is a 2p2, it is in p2 overtone, we take it as p2 overtone. So 2p2 plus 1 into by 4 into L 3L by 4 here into root t by mu. Now from this I can cancel these two, and L by 4 gets cancelled, 4 gets cancelled. From there I'll get 2p1 plus 1 2p2 plus 1 as 1 by 3. So this is the condition which it has to satisfy. Okay. Now let us check what are the possible values of P1 and P2 satisfying this condition. P1, P2. Now if I substitute P1 as 1, so if I substitute 3, so 3 is a 9, from there we will get it as 4, P2 as 4. Next, if I substitute P1 as a 2, let us check what values we'll get. So if I substitute it here, it will be 5, you'll get it as 7. So these are the minimum possible frequencies, right? In this case, the frequency, right, we'll substitute back in the frequency. Here frequency is F0, fundamental frequency. It will be P1, I'll substitute here. So it will be 3 by 4 into L by 4 into root t by mu. So this is the fundamental frequency, and this value is given as 100. Next, in this case, F1, let us say first overtone. So if substitute 2 is 2 here, so 2 2s are, in this case, let us say substitute 2 2s are 4, 4 plus 1 5 by 4 into L by 4 into root t by mu. So this value is asking. So from here, let us say x. So now we can substitute, or we can substitute from here 3 by 4L into, let us say this is x, and divide, let us divide them. So we'll get 3 by 5. So let us divide these two equations. So 3 by 5 will be equal to 100 by x. From here we'll get x value as 500 by 3. So this is the next possible frequency. So the next question, sources separated by 20 meters vibrate according to equations. Y1 is equals to 0.06 sin pi t and 0.02 sin pi t. Send out waves along a rod with speed 3 meters per second. What is the equation of motion of particle? 12 meters from the first source and 8 meters from the second source. Now if we take the sources, they are separated by S1 and S2, separated by distance 20 meters. Now I'll write this as x equal to 0, and this will be x equal to 20 meter. Now he's talking about a point which is 12 meters from S1 and 8 meters from S2. So this is the particle. Now we want equation of this particle, which is at x equal to 12 meter. Now here the equation of first particle, first source, is given by 0.06 sin pi t, and second source is given as 0.02 sin pi t. Okay, then here we can observe these two sources have equal frequency. So omega 1 angular frequency is same, means these two particles are coherent sources. Okay, now when two coherent sources are traveling in opposite direction, it will result in a stationary wave. Now, and velocities of both the waves will be same. Velocity is given as 3 meters per second. Now here, to find displacement of this particle, first of all let us write equation of wave from first source and second source. Now to write equation of a wave, we know when displacement of source at x is equals to x naught is given as f of t, y equal to f of t, then equation of the wave from this source is given by y is equals to f of t minus x naught by v when the wave is moving towards right, and similarly y is equals to f of t plus x naught by v when the wave is moving towards left, that is minus x-axis. Now using these two, let us write equation of waves from both the sources. So from S1 y1 is equals to 0.06 sine pi into t minus x naught in the first case is 0, so it will be x by 3. This is the equation of first wave, and from the second wave 0.02 into sine pi into, now it is moving towards left, so it will be t plus x minus x naught. So x naught in the second case is 20, so it will be x minus 20 by 3. So this is the equation of two waves. Now we have to calculate at 12x equal to 12. Let us substitute those two. So then at x is equals to 12 meter, the equations will be, at x equal to 12, the equations will be y1 is equals to 0.06 sine pi into t minus x is 12, so 12 by 3, 4, and y2 will be 0.02 into sine pi into t plus 12 minus 20, it is minus 8, so minus 8 by 3. So if I expand this to, so y1 will be 0.06 sine pi t minus 4 pi, and y2 will be 0.02 sine pi t minus 8 pi by 3. Okay, so here from these two, if I write this values, then y resultant at that point will be 0.0, this plus this, y1 plus y2. Now let me expand before that. So it will be 0.06 sine pi t minus 4 pi will be sine pi t. So 0.06 sine pi t will be y1, and y2 will be 0.02 sine pi t minus, here I can write this one as 2 pi plus pi by 3. So sine 2 pi plus pi by 3 will be sine pi by 3. So I can write it as sine pi t minus pi by 3. So you can rearrange using trigonometry and you will get it. So now the displacement, resultant displacement will be 0.06 sine pi t plus 0.02 sine pi t minus pi by 3. So this is the expression, and even you can further expand this one using sin a minus b as a sin a cos b minus cos a sin b. The next question, a wire made of material of Young's modulus 20 into 10 power 10 Newton per meter square is stretched by 0.1%. If its length is 1 meter and density of the material is 8000 kg per meter cube, calculate the fundamental frequency of the wire. So now here he is talking about a wave string fixed at both ends. Now we know expression for fundamental frequency in this case, f naught is equals to 1 by 2l into under root t by mu. Now we have to calculate t value and mu value. The length of the string is given as 1 meter. So now we have to calculate t and mu. So we know t, right, as it is stretched due to elasticity, we'll get the tension. So we know y is equals to Young's modulus is equals to f L by A into delta L. From here I can calculate the tension. Tension will be equal to y into A into delta L by L. So this is expression for tension. Next, we know relation between linear mass density and volume density. So mu is equals to rho into area of cross section. So now if I substitute these two in fundamental frequency, I'll get f naught as 1 by 2 into under root ya into delta L by L divided by rho a. So area of cross section cancels. So f naught will be 1 by 2 into under root y value is given as 20 into 10 power 10. into delta L. So here delta L by L. So here it is stretched by 1%, means delta L by L value is 0.1 by 100, that is 10 power minus 3. So I'll substitute here delta L by L is equals to 10 power minus 3 divided by density is given as 8000, so 8 into 10 power 3. So from this, if you solve, we'll get fundamental frequencies approximately 79 Hertz. So try to solve it. Next question, find ratio of fundamental tone frequencies of two identical strings after one of them was stretched by 2% and other by 4%. Just now we got an expression for frequency as f0 is equals to 1 by 2L into under root T by mu, and when an elastic string is stretched, tension is given by y into A into delta L by L. Here, and he is also mentioned here, tension is directly proportional to elongation, T is directly proportional to delta L. So now from here, you'll get f0 is directly proportional to delta L. So now f1 by f2 will be equal to, and here f0, sorry, it is under root L. So f1 by f2 will be under root of delta L1 by delta L2. Now this is stretched by 2%, this is stretched by 4%, so this will be equal to under root 2 by 4. Now from here I'll get f1 by f2 as 1 by root 2. And here he's asking the ratio of this one. So 1 by root 2 will be 1 by 1.414, it will be 0.7. So this is how to solve the question. Next question, a guitar string is 90 centimeters long and has a fundamental frequency of 124 Hertz. Where should be pressed produce fundamental frequency of 186 Hertz. So here he is talking about a guitar string. It is similar to a string fixed at both ends. Now we know fundamental frequency of this one is f0 is equals to 1 by 2L into under root T by mu. So this is the expression for fundamental frequency. Now this value is given as 124 Hertz. So this is the fundamental frequency in first case. Now what he is doing, you have to press somewhere such that the part of the string which can oscillate will be only this. So now the length of this one will decrease. Now let us say this length, total length is L, and let us say we have pressed at a distance x. Now L2 is x. Now we know from here, as root T by mu will remain constant, f0 is inversely proportional to length. So from here I can write f1 by f2 is equals to L2 by L1. This is how we can write. So from here he is saying f2 value is 186 Hertz. So f1 is 124 by 186 should be equal to L2 is x by L. So from here, and L value is given as 90 centimeters. 90 centimeter. So from here we'll get x is equals to 124 by 186 into x is 90. So x is equals to 60 centimeters. So you have to press at 60 centimeters from this end or 30 centimeters from this end, such that the frequency will be, fundamental frequency will be 186 Hertz. Next question, standing waves are set up in a string of length 240 centimeter, clamped horizontally at both the ends. The separation between any two consecutive points where displacement amplitude is 3 root 2 mm is 20 centimeter. Now he is talking about a situation where length of the string is at 240 centimeter and both ends are fixed. So here it is node and here also it is node. Now let us take a stationary wave. So this is, let us say, a stationary wave we have like this somewhere. Now he is talking about separation between two consecutive points where displacement amplitude is same. So let us take displacement amplitude to be same. If we take, these are the points where displacement amplitude is same. Now he is talking about this point, this one here and this one. Now these are the points with the same displacement amplitude. Now he is saying distance between these two is equal and it is equal to 20 centimeters. So this distance is 20 centimeter. And similarly here is 20 centimeter. So here we can say this from here to here, the distance will be wavelength lambda. So wavelength is 80 centimeter. So now here this part is 20, 20, 20, 20. So we got wavelength to be 80 centimeter. Now next, what he's asking? He's asking which overtone it is. So how to get it? As we got the wavelength and we know the length of the string, from there we can find number of loops in it. Okay, so each loop is of length lambda by 2, so that is 40 centimeter. Okay, now the total length of the string is given as 240 centimeter. From there I'll get number of loops as 240 by 40, it is 6, so 6 loops. So 6 loops means it is fifth overtone. So that is how to get the which frequency it is or which overtone it is. Next is also asking maximum displacement amplitude. So we know the expression for A in a stationary wave as some A maximum into sin kx. It will be in the sine function form. So A is equals to, so A maximum, so A value is given here, A value is given as 3 root 2. So 3 root 2 is equals to A maximum into sine k. K is 2 pi by lambda into x. So now let us substitute. So 3 root 2. 1 minute. So 3 root 2 is equals to A maximum into sine 2 pi by lambda is 80. So we know 3 root 2 at a distance, this distance will be 10 centimeter. So into 10, 80 into 10. So from here we'll get pi by 4. So 3 root 2 is equals to A maximum into 1 by root 2. So from here A maximum is 6 mm. So this is how to solve the question. Guys, if you have any kind of doubt, please let us know in the comment section. I'll try to solve it as soon as possible. Guys, if you find this video helpful, please hit the like button. In this series, I'll cover entire JEE syllabus. And apart from physics lectures, we will be coming up with exciting videos on career guidance, like review videos on engineering colleges and detailed analysis of all branches. And we are also planning to share informative videos on entrepreneurship. So if you don't want to miss out on these videos, please subscribe to our YouTube channel.